Session of this conference in granular flows. Our first speaker is also one of our organizers, Hrenya, and she's going to be talking to us about instabilities in the homogeneous cooling of gas solids.
Thank you. I'd like to start. Can everyone hear me in the back? Great. I'd like to start just by thanking the organizers for putting this together, as well as all of you for being here today. I'm going to talk a little bit about some work my group has been doing in collaboration with a collaborator, Professor Yin, who's at the Colorado School of Mines. Many of you were at Golden. That's in Golden, Colorado. It's about half an hour south of us at CU Boulder. In Zhalong's contribution in this work, I feel like this has just gone off. All right, I'm going to have to do without this. I'll talk about a little bit more. He was in charge of the direct numerical simulations that we used. My other co-authors at University of Colorado were John Zank and Peter Metrano. John Zank's an former undergraduate in my lab, and Peter Metrano is a current PhD student. So I'd like to motivate this work a little bit because most of the folks here are familiar with instabilities in granular flows. And what we were looking at was towards extending this work to instability seen in gas-solid flows. In a typical application, we've shown here is a circulating fluidized bed. So this is where you have a gas being fed at the bottom of this fluidized bed. In conjunction, you have solid feedstock being fed from the left. Both are traveling upwards. They're separated at a cyclone. The gaseous product is separated from the solid particles, which can then be regenerated and refed to the circulating fluidized bed. And what you see in this freeboard region, which is above this dense bed right here, are the formation of these streamers, ribbons, or clusters as we call them. And they're very similar to the clusters we see in granular system. They're transient, they continue to evolve and break up with time. So very dynamic in nature. So when we think about clustering in these gas-solid systems, there's been quite a bit of work in granular systems about the origin of such instabilities, as well as in systems with gas, but not considering the dissipative mechanism in granular flow. So what I'd like to do is first start by overviewing these two. So I've put up first the iconic image, really by Isaac Goldhirsch. And this is a homogeneous cooling system in which the particles, this is a molecular dynamic simulation, the particles were initially randomly distributed, and then you see with time that these clusters form, and that is due to the inelasticity associated with those collisions. So the fact that the collisions are dissipative in granular or kinetic energy is why you see these clusters. If your restitution coefficient were equal to 1, they would never develop. We've also done some recent work showing the same can be true with friction, and that there's also an interesting interplay between these two. But basically, friction and elasticity are sources of dissipation, and that's what's causing these clusters to form in this granular system. So let's look now to what's been done in gas-solid systems. In gas-solid systems, this is actually a simulation from a two-fluid model by a student at Reeson's group in Princeton. And it is of the freeboard portion of the reactor that I just showed on the previous slide. So you see similar types of transient high particle concentration areas. And what folks who have done work in instabilities in these gas-solid fluid system have focused on instabilities arising from the fluid phase. And they can arise from either mean drag between the gas and solid phase or from viscous damping. Due to the fluid. So what we're trying to do in this work is really assess the relative importance of both of these mechanisms. So knowing that when we have a gas-solid mixture, it's not just gas phase effects which leads to instabilities, but there's still the dissipative nature of particle collisions there, and what role does that have relative to the gas phase effects? Those two have never really been looked at back-to-back for these typical circulating fluidized bed conditions. And so our approach here is to do direct numerical simulations, and this is the part that Yin, my collaborator, is an expert in. And he has done those for gas-solid flow using a lattice-Boltzmann type model. It's a model that actually traces to Tony Ladd at University of Florida. I think several people in the crowd are familiar with that code. We did some work in molecular dynamics in the granular limit to test the limit of that. And then we're also doing, although we did it here just for more verification of our numerical codes, we've also done some preliminary comparisons with a new continuum theory for these flows. So that's what I'd like to talk about the rest here. So with regards to the typical conditions we're using, or the parameter space we covered, these are typical conditions found in a circulating fluidized bed reactor, like I showed in the first slide. So we're looking at restitution coefficients between 0.8 and 1, solids fractions between 0.1 and 4. The system length scale, note I put up here 30 by 30 by 40. We're actually using fairly thin. That's just due to the computational overhead associated with the DNS simulations. They take considerably more time if we were to do an L by L by L or a cubic domain. We did spot check the cubic domain, and so the results I'm showing here are representative of what you get in a cubic domain as well. We feel confident that way. It's just most of our production run simulations were actually done for a relatively thin box. The dimensionless groups I have highlighted in blue are those that arise because we are looking at a two-fluid system, namely a gas-solid system. So we have a density ratio between the solid and fluid that is on the order of 1,000. Again, that's typical for gas-solid. So we're not talking about liquid-solid suspensions here. This work is restricted to gas-solid. And then finally, a Reynolds number. And note this is a Reynolds number which is proportional to the fluid density as well as the square root of an initial granular temperature. Or in our case, an initial kinetic energy. So this is a ratio of the particle inertial forces to the fluid viscous forces. So as I have a Reynolds number towards infinity, that's the granular limit. Whereas I have a Reynolds number towards 0, that's totally dominated by the fluid. And again, typical ranges for these circulating fluidized bed reactors are in the range of 3 to 30, because that's where we really wanted to focus our attention. So the system we're looking at is the simplest one out there, essentially, because we really wanted to be isolating the physics we were interested in. We're looking at a homogeneous cooling system. And what this implies is we have periodic conditions on every side. There's no external forces. So the energy or the temperature of the system decays with time, just due to losses either from particle-particle collisions or particle fluid. This one says 3D domain. Remember, though, I said it's very thin. We have a random initial configuration and no net momentum to start with. So that's the homogeneous in the homogeneous cooling system name. The particle properties, we basically input restitution coefficient. We're assuming a monodispersed suspension and frictionless particles. So with that in mind, I want to talk a little bit about the work that's done in instabilities for the two extremes of the systems I described early on. So the first work is that associated with what Isaac Goldhirsch had published for the homogeneous cooling system. And what he found is that if you start with a random configuration of particles and also at random velocities, and what we're showing here is a cone plot with coarse grain velocities. So you see these arrows are randomly distributed. That means there's no instabilities initially, and we're starting it out in that random configuration. If your system is large enough, and again, it has to be large enough for instabilities to develop, just like you have to have a large enough Reynolds number for turbulent flow to occur. But if your system is large enough, you can get these velocity vortices, which we see in the center picture. So you see more of an aligned motion of that coarse grain particle velocity field. And then at later times, again, if your system is large enough, now what I'm showing here are just where the particles are located. You can see these clusters, which are these dynamic collections of particle that continuously form and break up. So that's what's known for the HCS of granular systems, so no fluid phase. There had been some work by Koch just over a decade ago on gas-solid systems, but they assumed that they had elastic particles. So they were really focusing on instabilities that occurred just due to the presence of the fluid phase. And again, remember, we want to compare and contrast those two for realistic applications. In what they found, this was taken from their work. So this is a dimensionless neighbor distance versus time. So in this region, we see that the distance between neighbors is relatively constant and a little bit noisy. That's just reflective of their initial random condition. At longer times, they're reaching a constant dimensionless neighbor distance, and it slowly decreases to here. So this is obviously the clustered region. What they didn't report on, they showed snapshots in time like we did up above, and this was just reproduced using simulations in parameter space similar to what Isaac had done. What they showed here were concentration fields, but they didn't report it all on a velocity field. So one of the questions we have is, are we seeing a velocity vortex instability which precedes the particle clusters? That's one of the questions we ask, in addition to just the relative nature or the relative importance of these two mechanisms in a gas-solid flow where you didn't have elastic particles. So again, both of those dissipative mechanisms were present. So I mentioned the focus of this work was really on using simulations to help us answer this question. But to verify our code in applying to this system, we also wanted to compare with a hydrodynamic theory. It's just one of the pieces of verification we did. For a homogeneous cooling system, you only need to look at your energy balance. That's the only non-trivial balance, if you will. And so on the right-hand side, we have the cooling rate, which we have in granular systems. That's just due to the inelasticity of particles. The second term on the right-hand side has to do to the viscous effects associated with the fluid. Typically, there's going to be a third term on here, which is the source due to mean flow between the gas and solid. But because this is a homogeneous cooling system and we're starting out with zero mean velocity for both of them, that term goes away. So this is simplified to the homogeneous cooling system. So we wanted to do this, like I said, our motivation for comparing with the hydrodynamics was to verify both the DNS and the MD simulations initially. We're also detecting in time when the instability occurs, both for velocity, vortex instability, and the clustering instability. So we wanted to check the method we did for that. It was a Fourier-based method. We could do that by comparing with this hydrodynamic theory, because this theory is for a stable system. Obviously, there's no gradients here in X, Y, and Z. And when I start to get that instability, I'm missing some of that by applying such a simplified balance. So when those two tend to diverge, and by those two I mean the hydrodynamic predictions from the simulations, that's when I know that instability sets in. Again, we're detecting it via Fourier method. We're not using that as our detection method, but that helps us check this. And finally, although and I don't want to focus on it here, there is a new theory that was done in conjunction with Vicente Garzo, who's here as well, for gas-solid systems. The kind of new aspect of this is that there was an instantaneous drag force incorporated at the Enskog equation level. And so we also wanted to use this as preliminary, very preliminary, I should say, validation for that theory as well. And so our first comparison between the simulation and theory is shown here. So on the y-axis, I have a kinetic energy, which is non-dimensionalized with its initial starting value. Along the x-axis, I have a dimensionless time. So you see for all of these, I have a decay of energy of time, which I'd expect. The simulations are shown in the dotted line, in the hydrodynamic theory is shown for these two. And I am looking, one at the granular limit. So this is the granular flow, then I add the fluid, and these are the two corresponding. So clearly when I add the fluid, I see it's changing from the granular flow and its decay rate, which is at least telling me that fluid's important, just very initially. The diamonds here that are shown for each of these lines in the DNS data, as well as the MD data, is where we detect the vortex instability to onset. So this is where you start seeing a separation between the kinetic theory predictions and the simulations. So that detection mechanism, it's initial verification for that. So again, this is really just for verification of our code as well as the theory. They go hand in hand, and shows that the two do agree before the onset of instability. So with that in mind, we wanted to start looking at this balance between the granular dissipative mechanisms and the fluid dissipative mechanisms in giving rise to these instabilities. But we first wanted to take a look at what sorts of instabilities we have. So these are snapshots of the coarse grain velocity field on the bottom, particle locations on the top. Going to left and right, we're just progressing in time. So although this is an initial time, it's a little bit later than initial time. The dimensionless time is given up here. We see that both the particle concentration as well as the velocity field is still fairly well randomized. What you see then as you increase in time is that you start to develop a vortex instability, but your particle concentration is still fairly random, okay? And then as we progress even further in time for a system which is large enough, we have both the vortex instability as well as you start to see some non-local distribution of the particle concentrations as well. So we see, and this is the first time we've seen in gas-solid simulations, so these DNS-type simulations, that we actually have a vortex instability present before the clustering instability. And that mimics what was seen in the granular system as well. It's just that this had not been reported before, but we do see that same progression. So with that in mind, not too surprising there, what we're looking at here is a ratio of collisional to viscous dissipation. So at the horizontal line is a value of 1, where those two mechanisms would balance one another. So let's just look at the red lines first. For the red lines, I have two different restitution coefficients for the same Reynolds number. The Reynolds number here is 30. The top red line is a restitution coefficient of 0.8. It lies above the solid red line. So that's saying that collisional dissipation is more important for higher restitution coefficients, which again makes sense. You have higher dissipation associated these, and these are instabilities which are traced to dissipative effects. The same is true as we go from that high Reynolds number of 30 to the green sets of line and then the blue sets of lines. What's happening there is we're decreasing the Reynolds number. That means we're increasing the viscous forces relative to that particle inertia. And so we see that the role of viscous dissipation starts to play more of a role, as you'd expect. So again, not a whole lot of surprises to this point, except that our original question was largely answered, saying that both the dissipative mechanisms as well, or I should say the inelastic or particle mechanisms as well as the fluid mechanisms both play a role in instabilities over this range of parameters that's typical. So the next thing we want to look at is the energy dissipation prior to instability. So this is before we see a velocity vortex onset or a or clustering onset. And a couple of things to note about this plot is basically before the instabilities, if we have both dissipative mechanisms, a system is going to lose energy quicker than if it had only one dissipative mechanism. Again, this isn't too surprising based on what I've already shown you. So if I look at the top set of lines, the restitution coefficient equal 1, is I go from the solid black line, which is basically a value of 1, and go to higher Reynolds number. So the red is 30, excuse me, as I lower the Reynolds number. So the granular, the black line on top, and I apologize, my pointer just burned out right before this. That black line right on top is the granular system. As I go to the red sets of circles, is there another one here? Oh, the old-fashioned way, the stick. Okay, thank you. Thank you. Okay, so this is the granular system. Then I'm going to a Reynolds number of 30 and 3, so I'm increasing the fluid effects. I increase my dissipative rate. Similarly, as I go from this set at E equal 1 and increase the dissipation associated with the inelastic collisions, I'm going to increase my dissipation rate as well. So again, pretty consistent with what I'd expect. What I'm showing here is when the instability actually onsets. So the previous graph was prior to onset. Now I'm showing onset. This graph has a lot going on. So what I'm showing here is the pink line is a gas-solid system with a restitution coefficient equal to 1. So I just have viscous dissipation effects, no particle-particle dissipation effects. This is the opposite. I have a granular system with just particle-particle dissipation, but there's no fluid phase. And then this is combined. So again, this has the higher energy decay rates. What each of these are showing, each of these diamonds, is for a different simulation, so for different starting conditions, when I detect the onset of that instability. Of course, it's going to be slightly different for different initial conditions. What this vertical line is showing the average over many simulations, and we did enough simulations to show that those were statistically significant. So what you see then is that blue vertical line, which represents the gas-solid or both dissipative mechanisms. You have the onset of the instability quicker than you do for just the granular system than you do for the gas-solid system. So again, both of these mechanisms are playing an important role in giving rise to these instabilities. What's surprising is in this graph. And what we notice here, if we follow any of these lines again, the red bottom line shows a gas-solid system, so it has the highest energy decay rate. Up here is the granular, and up here is a gas, but with perfectly elastic particles. So the largest decay rates when I have both of those mechanisms. What's happening is I eventually get a crossover of kinetic energy. So that means the most dissipative system, at later time, can actually achieve higher energy levels than the least dissipative counterpart. Okay? So why is that happening? It's surprising kind of at first glance, but if you think about physically, the physical picture we've developed with regard to these velocity vortices, it makes sense. And so what do I mean by that? Well, as we increase our dissipation level, what's going to happen, what we saw a couple of plots ago, is that the time to velocity vortices decreases. It makes sense because you're losing more energy quicker, and that's what's giving rise to these instabilities. Those instabilities imply that we always see that velocity vortex instability first. So that means we have an aligned motion of particles once that instability comes on. And what happens then is when we have more glancing particles, you're not as likely to decrease as much energy as if there is a distribution of angles which the particles collide at. Because remember that restitution coefficient impacts the normal component of the velocity, not the tangential. So if you have preferred tangential or glancing collisions, you're going to lose energy quicker. So those systems which lost energy very quickly initially then slow down their rate and can actually achieve higher energy levels than their non-dissipative counterparts. So with that in mind, I'll just put up the conclusions here without reading them in the interest of time, and I thank everyone for their attention.
One or two quick questions.
So the system is continuously cooling.
That's correct.
So maybe there's something I missed where the Reynolds number definition comes from.
So the Reynolds numbers continues to decrease with time as well. Is that what you were asking? Associated with the random motion? Yeah.
Because
That's
you
correct.
presented the curves at constant Reynolds number, right? Or you didn't?
Initial resistance.
It's the initial, thank you. That's right. The Reynolds number, which I was putting in the legend, is the initial Reynolds number. That's right.
Yeah, great work. Can you go back to the velocity fields? I just have a quick question, and probably misunderstood from at the very beginning.
From just the picture of the velocity
Yeah,
field?
so just the planar, there you go. It seems to me that you're right, when you have vortex and plus instability, you have a much more smooth flow or than the one in the lab. Does that mean that you're subtracting the mean flow? Is what I'm seeing is just the structure?
So there is no mean flow that we're beginning with.
Okay.
So we initialize the system with random velocities, make sure we do an overall momentum check and subtract out anything that would be a mean flow. So this is just associated with the structure.
Okay, all right, so that makes sense.
Yeah, I think we need to move on in the interest of time. Thank Christine once again.